Hi, my name's James, and today we're going to be talking about logic. What I have here, this little picture, is of a transistor. The way that a transistor works, and this is the type of transistor that's in a computer or in a lot of electronics, is it has some kind of input and some kind of output. Whether or not the signal gets carried from the input to the output is dependent on a third part here, and that decides whether or not it's going to go through. So it can either be off or it can be on. If it's off, then the signal stops and it doesn't make it to the other end. If it is on, then it will go all the way through the transistor. Using these transistors, you can do mathematical operations, you can do all sorts of things. So if we start with the basic logic operations that occur, we would start with, let's say, an AND. An AND is where you want crackers and dip. You can't have the crackers or the dip. You can't just have one or the other. If you want to eat crackers and dip, you need to have both things. The way we represent this as a symbol is we do a little upwards chevron, which is essentially the A of an AND if you were to draw a line across it. This is our little AND. And the way that this would be represented in terms of the little transistors we were talking about is we'd have one source, it'd have one transistor, and then it would have a second transistor. The charge only gets carried across from one end to the other if this transistor is on and this transistor is on. If we only have one on or the other on, only one of them, then the charge is not going to make its way all the way across. It's kind of like if you had a hallway and you had two doors, one after the other. You need to have both doors open to walk the entire way down the corridor. So that's our AND. Another option is OR. An OR is the opposite of the AND visually. And the OR is something like, I can have chips or I can have olives to snack on. You could have both. You could have one, you could have the other. But you want the snack, so you can't have none. If we look at this as a diagram of the transistors, you have one source. This splits off into a first transistor and a second transistor. And then these join back together again at the very end. If you have this one on and this one on, the signal comes through both sides and it comes out the other end. If you only have one on, this one, and the other one's off, then the signal will carry through this side and it will pass all the way to the output. And if you only have this one on, same story. So this is why it's OR. It's both, it's one, or it's the other. That covers the two basic logical operators and an OR. We have a few other ones we can look at as well though. We have a NOT. Whichever the input into a NOT is, we just flip it. So if you get a 1, it becomes a 0. If you get a 0 as an input, it becomes a 1. And this is represented by either this little line here, or sometimes in code, you might see it as an exclamation mark. One that's really common in computing as well is called an XOR. And a regular OR is this, or that, or both. An XOR is exclusive OR, so it's this or that, but not both. If you were walking down a hallway and there were two doors at the end, you could go through the left door, or you could go through the right door, but not both doors. So let's take a look at how this would look as a Venn diagram. We have A, we have B. If we put something here, then we would say A is false and B is true, because it's inside of B but not inside of A. If we instead were to put it here, then we would say A is true and B is true. Make sense? And is this section in the middle. It means both A and B have to be true. If it's over here, then it's not AND. If it's over here, then it's not an AND. It has to be in this middle section. An OR, a regular OR, not an exclusive OR. We can also sometimes call this an inclusive OR, but we will just say OR. This can be anywhere in either of these circles. Let's just do that in another color. So OR, that can be anywhere in here, and anywhere in the middle. Meanwhile, an exclusive OR is a little bit different from this. An exclusive OR is also this entire section and this entire section, but it's not the middle section. This part in the middle does not count for an exclusive OR. So it can be here It can be here, but it can't be in here. And that's an exclusive OR. The last thing we'll look at in logic is implies. So with implies, we have this little symbol. And this is to say, this thing implies that thing. For example, if a government official is bribed, then that implies that he is corrupt, right? Now, the thing with implication is you should never think that implication can be reversed. If the government official is corrupt, you can't assume that he's been bribed. He might be corrupt for different reasons. For example, he might be blackmailed. So the thing with implication is it's very one-directional. If he's bribed, then he's corrupt, right? But from that, you can't say if he is corrupt, then he's bribed. That doesn't follow. If you make that statement as well, if you say if he is corrupt, then he is bribed, you can combine them into what's called logical equivalence. But we won't worry about that for now. We'll just stick to implies. So when are these useful? One place that you're going to see a lot of it, especially if you're doing some programming, is if statements. If A and B, then do C, right? Makes sense? You might also have if A or B, then do C. And this is where it comes in handy to know these sorts of things. Because, for example, you might want an XOR, an exclusive OR. You might want it that if only A or B, but not both, then do C. So it's important to understand these concepts when you're writing your code. Another one is with databases. You could be saying if this client lives in Australia or New Zealand, you might want to be checking that. But you might also want to be checking whether they're in both, because there might be an error in the system or something. So thinking about these things in terms of logic can often be quite helpful. So let's look at some examples. Imagine I'm a Twitch streamer. I will wear bunny ears on Twitch if I receive a donation or if I get a new subscriber. Now, how would we write this out? We use a letter to represent the thing. So, for example, B, let's set that to bunny ears. Let's set S to subscriber. And let's set D to donation. So we can now write out sentences using the notation we learned earlier. The and, the or, the XOR, the implies. So let's apply to this statement. I will wear bunny ears on Twitch if I receive a new donation or if I get a new subscriber. Okay, so subscription or donation, that's our or. Now, bunny ears. So I said the bunny ears would be because of the subscription or donation. While it was first in the English sentence of it, if we were writing it out in a logical notation, we wouldn't want to write the implies backwards and write it over here. We'd probably want to write it over this side, which would mean that if you read it out, it would be a subscription or a donation implies bunny ears. Now for another one. If it is raining and I'm outside, then I'll need an umbrella. First of all, we have is raining. So let's set rain equal to little r. I'm outside. Let's set that to a little o. And needing an umbrella, let's set that to a little u. Which logic notation do you think this be? Do you think it's an and? Do you think it's an or? An XOR? If we're not outside and it's raining, we don't need an umbrella. If we are outside and it's not raining, we don't need an umbrella. That means that it has to be both at the same time, which is an and. Rain and outside implies umbrella. Let's try that again. Actually, let's go back to the rain example and try looking at it there. So for a truth table, what we're looking at is every possible combination of whether one variable can be true or false, or the other variable can be true or false. So let's have rain. Let's have outside. So true, 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 false, false, true, false, false. And now let's look at the sentence or the logical statement we had over here, which is rain and outside. Rain, true, and outside, true. The and is saying that if both of these are true, then it's true. So that one is true. Rain is true and outside is false, which is it is raining, but I'm not outside, therefore we don't need an umbrella. So that's false. And then we have it is not raining, and I am outside, so we do not need an umbrella. And then lastly, we have it is not raining and I'm not outside, so we don't need an umbrella. So that's more or less how you do a truth table. We can also do this with the or over here. So we have the S and the D. We have true, true. False, false. There we go. And we have the sentence, which is S or D. Now, if S is true and if S is true and D is true, which we have here, true, true, then or, the regular or, can be true. If one of them is false, it's okay, it's an or. We only care if at least one of them is true. This would be true too. This is the same thing over here, this one. But if we have neither true, then this is a false. That's how the regular or works. So we haven't done an example for the XOR written like this as a sentence, but let's do a truth table for it. We have A and we have B. We have A XOR B. True, 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 false. There we are. We know that the property it has, like a regular OR, is that if one of them is true, then the answer is true. So we know both these are true. Like both and or, we know that if you don't have either input, if it's both falses, then it's false. And there's a difference between this one and the regular OR. So the regular OR, we would have had true and true implies true. However, with the XOR, we know it's not and. It's not when you have both. When there are the two doors, you can only pick one. Which means if we have this true here and this true here, that actually is a false here. So we have false, true, true, false for XOR. Let's do something a little bit extra on this, extend a bit further, and look at not A XOR B. So what do we have to do if we have a not at the start? Well, we just have to look at the opposite of the previous answer. The previous was false, and now we're flipping it, so it's true. And then you just repeat that for each one. So now that we've looked at truth tables, which are one way of writing it, let's look at a slightly more computer sciencey way. So we've got our trues and falses. The true can also be written as a 1, and the false can also be written as a 0. This whole table could just be turned into ones and zeros. So we have some binary here. We have some binary here. These are our two what are called bit strings, because it's a string of bits. And we want to perform an operation on them, as in a logical operation. Let's look at and again. We'll just write it here. Now what you do is you perform the same thing we were doing over here with the truth tables, but we do it each element by element. We've got a 1 and a 1 just here, so we write that as a 1 in the final answer. We've got a 1 and a 0 here, which is a 0. 1 and 1, 1, 0, 0. There we go. So that would be our answer for a 1 and 1. It would be quite similar if we did an OR. So we've got our OR here. We've got 1 or 0, 1, 1 or 0, 1, 1 or 1, 1, 0 or 0, 0, or even an XOR. That's a 1 because it's 1 and 0, 1 and 0. 1 and 1, it's XOR, not a regular OR. So you can only choose one or the other, but not both. So in this case, 1 XOR 1 would be 0, and then 0, 0, 0. And you continue that forward. So that more or less covers the basic logic operations, and, or, XOR. Now this can be used to do some really interesting stuff. For example, addition in computers is almost entirely done by using an XOR and an AND. Now, you might remember from a previous episode when we talked about adding, or we talked about numbers with binary, converting between binary and decimal. So that means that the way a computer actually adds two decimal numbers together is it performs these sorts of logic operations on 2 bits of binary, puts them together, and then uses that to work out a final answer in decimal. We'd say we'd add 1 and 0 and we'd get 1. We'd add 1 and 0 and get 1. We'd add 1 and 1 and we'd get 0, and we would carry the 1, and we would get a 0, we'd carry the 1, which is now 1 and 0 and 1, which is 0 because we're adding these two together. We carry the 1. We go 1 and this 1, which is 0 again, we carry the 1. Then finally we end up with a 1 and a carried 1. So the answer to adding these two together is 1, 1, 0, 0, 0, 1, 0, 1, 1. Now how that's actually done, for those who are interested, is you are actually taking an XOR between these two, and then you're also using the output of an AND for the carrying digit. But don't worry about that if it seems too confusing for now. Another thing that these are used for is cryptography, as in storing passwords. If we have a secret word, such as banana, and we have another word message, well, we need to make it bananas, what we can do is we can actually XOR each of these letters. So you can XOR the S with the E, you can XOR the A with the G, and that means that only if you've passed this message to the other person bananas can you work out from the jumbled answer how to get back to the original message again. Finally, another really cool application is a lot of how you store memory in RAM uses not and not or. There's this cool little mechanism you should check out sometime where you cross the outputs of two NORs or two NANDs, and you can actually permanently store a bit of data. So between the XOR and the AND for addition, and the NOR and the NAND for storage, that already gives you the basic building blocks of how you make a CPU. So if you want some practice for both the logic section and the basis section, one thing you could do is you could take two numbers, and then you could convert them into their binary, try and add them together, and then turn them back into their decimal again. A 6 will become, if we remember from last episode, 0, 1, 1, 0. Now there's our binary. Now we have a 2, which will become 0, 0, 1, 0. Now we add these two together. 0 and 0, 1 and 1, carry the 1, 1 and 1, carry the 1, 1, 0, 0, 0, which is 8, because it would be in this column. Another one you could try, as a bit of practice, is something like taking two numbers, such as 6 and 2, and performing a different operation, like an XOR, or an AND, or an OR. I'll leave you with a couple of ones to try, and I will put the answers below. So let's try 7 XOR 3. Let's try a 2 and 3. There we go. Have a crack at those.